Hello, friends. Happy to be here with you today. Wanted to share some stuff with you right quick. I'll go ahead and get my screen shared here. Okay, so I want to talk about section 3.3 with you for just a second. And so I was doing some work. Let's see if I can get to the right spot. There we go. So section 3.3, we're going to be doing problem number 15. Okay, so let's go and see if we can find 3.315. Here we go. It says, what is the largest n for which one can solve within 1 second a problem using an algorithm that requires f of n bit operations where each bit operation is carried out in 10 to the negative ninth seconds with f of n? Okay, so this is one where the jargon, the word problem, makes it a little bit confusing. But what I want you to see is that there's actually a little bit of relationship between these. So instead of beating our heads against this for too long, let me see if I can make an adjustment here. Nope. All right, let's go to fit. All right, so let's see if let's just look at what the answers are to this question. So I'm going to bop over here, and here we are in section 3.3, and I'll come up here to question 15, and it says for part A, it's asking the log of n. So if f of n takes 10 to the ninth operations, log of n, they're saying you need to think about base 2 to the power of 10 to the n, which is basically or approximately 10 times 3 times 10 to the 8th. Now, for me, I don't like answers like this. I feel like that's leaning on you to have a very, very good understanding of exponentials and logarithms and things. And I understand that we all went over that stuff in high school, but the flip side of that for me is it's a stupid big number. And so that's what I want you to take away from this is if it's just the log of n and we're already doing like a billion operations in a second, it's going to be a really, really big number. Now for B, if we can do a billion operations per second and the function is carried out on the order of n, it's going to be about a billion operations. And so, yep, 10 to the ninth, a billion operations. Now, the next one we have n times the log of n. So it's not quite n squared, which would be the square root of 10 to the negative ninth, but it's going to be something smaller than we had for part B. So part B was 10 to the ninth, and part C is 3.96 times 10 to the seventh, which is a little bit smaller than 10 to the ninth. The 3.96 out front, I don't care about that as much. What I want you to see is if something is growing at the rate of n times log of n, you're not going to be able to get as much done. And the one that I think makes more sense now is part D. So if n was 10 to the ninth and C is 10 to the seventh, D should be 10 to the fifth, maybe? We'll go see what it says. Part D, 10 to the fourth. My apologies. Okay, so it's scaling down a little bit, and I'm guessing there's some math tricks in there to get us to that. Now, part E is 2 to the n. So that's going to be some sort of a log of 9 or something like that. So 2 to the n is scaling up really fast. So the answer for that, part E, is just 29. And then F, n factorial, that's 12. Now, I'm going to be honest, I don't necessarily understand. I haven't taken the time to slow down and understand the math of all of this. What we're talking about is we're trying to think through how many operations can you get done. And so when they talk about something is on the order of the log of n, that means it's going to scale nicer than something that's on the order of n. And if something is n log n, it's going to scale, and it's going to scale, but not quite as nicely as something that scales on the order of n. And so the idea, or the concept, what you're supposed to take away from this whole question is, as you go towards algorithms that scale more and more poorly, that means as you get to bigger and bigger problems, they're going to run slower and slower. So if something is scaling on n factorial means this sucks. You've basically hit a brick wall, and this is really not a solution, or at least not a very feasible one. And there are problems like that that we actually do solve. And that's why we have supercomputers. And that's why I love conversations like this. But at the end of the day, the reason why I don't spend a whole lot of investment, I want you to understand some algorithms are better than others, and some algorithms are going to scale better than others. And if you can get something that scales on log n or n, that's great. If you don't get something that can scale if it's less than n squared, that's still good. If it's n factorial, that's horrible. You need to look for a new algorithm if it's possible. But that's what I wanted you to take away from this part. Now, 16. It looks like it's basically the same question, but it's saying, what is the largest n for one can solve, for which one can solve within a day? So this time we have 24 hours using an algorithm that requires f of n bit operations, where each operation is carried out. Oh, sorry. That's my reminder to go get my my little people. Now these operations are getting carried out even faster. And so again, we're going to have a number. All right, so let's go look at, it's going to be log of n and then 1,000n. So this one's going to be, we're going to get a bunch done. We're going to get less done. We're going to get even less done, even less done, even less done, less and less and less. And so the concept is some of these are going to scale horribly. But let's see what the back of the book says. All right, so if each bit operation takes this much, we can carry 10 to the 11th. So 3 is 1,000, 6 is 1,000,000, 9 is 1,000,000,000, 12 would have been 1,000,000,000,000. So this is 100 billion operations per second. Therefore, blah, 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 operations per day. So 10 billion operations today, almost 11 billion 864. So that's 86 trillion operations per day. Therefore, each case we want to solve the inequality for n and round down to an integer. Obviously, a calculator or computer software will come in handy here. All right, so you're solving f of n equals 864 times 10 to the 13th for n. Okay, so this one's not a great one, but oops. My Zoom just let me know that it's logging me out. So must have been inactivity. Anyway, friends, the concept of that third problem is just this. How big is your n? And that's how the problem scales. And let me see if it hasn't kicked me out yet. So we'll just keep trying. Oops, screen 4. There we go. Oops. Okay, so what it's saying is you're going to have this number equals whatever f of n is. And this is our f of n. So f of n is the log of n. Well, what does this mean? You take, say it's 10 to the power of this. So it's going to be 10 to the power. Oh, I need it back here. So it's 10 to the power 864 times 10 to the 13th. That is a really big number. But it's a smaller number is going to be this number. So you take this number, divide it by 1,000, you're left with n. So you take this number, divide it by 1,000, which is minus 3, so it's 864 times 10 to the 10th. You take this number, you take the square root of it. Well, you take the square root of this. I don't know what that is for sure. The square root of 1 times 10 to the 13th. Probably an interesting thing to see. This time you divide it by 1,000 and then take the square root. This time you do the cube root. This time it's log base. You take log base 2 of this number, and that'll get n times log base 2 of 2, which I think that is 1. And then you take log base 2 of the other side, and you should be good to go. And now you're going to take that and then divide it by 2, and then even more fun math. So the concept is, this one, I'm not looking for any exact number. You could draw a graph, you can work through it on your own, but this is one hopefully where you don't waste too much time unless you get excited about this. Okay, and then finally 3.3, part 17, what's the largest n for which ones can solve in a minute, algorithm f of n. Again, this is going to be a very similar type conversation. So we can come in here, I think it's this one. Oops, my number 17. So we come down here, similar conversation, big numbers, slightly smaller number, slightly smaller number, slightly smaller, 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 smaller. And finally we get down to just a few operations in a minute. Well, friends, I'm going to go ahead and stop my share. Listen, a lot of fun to be had. I don't expect you to become experts in big O notation and things like this. It's a lot to get your heads wrapped around. But the general concept is we're going to have a problem set that we're going to be working through. And once that problem set gets large enough, one algorithm is going to run faster, one algorithm is going to run slower. Real world application of this. Let me talk about that for just a second, assuming my video is still here. Let's say you're going to run a for loop. For loop to do math operations. A for loop versus a parallel for loop. If your loop size is like 5, 10, your for loop is going to beat a parallel for loop. If you get out there to like 10,000 iterations, a parallel for loop is going to start to win, start to run faster. What that means, there's a little bit of overhead required for you to set up a parallel for loop to split it across multiple threads. But once you get up past that threshold, it doesn't matter how much further past that threshold you go, a parallel for loop is always going to be faster than a sequential for loop. Burning one core is going to be slower than burning all the cores if your job is big enough and your code can take advantage of it. And so that's an application of big O notation. My hesitation on big O notation, I'm personally an HPC guy, and so my personal beliefs, not to push them on you, big O is great. It's a great way to have a conversation. It's a great way when you're looking at theoretical, what should we look at first? But at the end of the day, there's only one guarantee that you have to know how long it takes you to get to an answer. And that is good old wall clock time. And so if one algorithm is x cubed and one algorithm is x squared log of n, or x squared log of x for their order, then I'm going to tell you maybe it's a foot race. But then the next question is, but are you operating in a problem set that's significant enough to take advantage of that? And so a great example of this is weather forecasting. Weather forecasting, you can almost definitely run a single cell, a single calculation locally for one spot faster on a desktop single thread computer. Because supercomputers, in order to get those to run, there's so much overhead to get it across an entire supercomputer. And it goes through a lot of switches and things. And so, but the flip side of that is if you want to do more than just a single spot in time, like you want to do an entire state, you're almost always going to be worth it to go to a supercomputer. That's what big O notation kind of helps getting you thinking about, kind of helps you start thinking about algorithms and the growth, the order of growth of these algorithms. It's a lot of fun. And for the folks that are really enjoying math and really enjoy getting to solve these things and getting, flex the old arithmetic muscles and the logarithms and things like that, I encourage you to have a lot of fun. For those of you that are a little less thrilled about this, slow down, take it easy. You're going to do fine. All right, friends, that's all I've got for you today. Thank you so much for your time. I hope you have a wonderful week, and I look forward to seeing you again real soon. Take care. Bye.